string theories, which might be the next thing. They were just having a heck of a time doing their math. There's something called set theory in mathematics that there was no reason for set theory. They were just like, this is a cool thing that we can do to make our brains really big in our head, right? You know, and the physicists go, I bet we could use that, right? And so now that's like one of the classes they take. They're doing set theory. They're learning set theory. So this is, I don't know. I guess this is all theory of knowledge, isn't it? Yeah, it's kind of, there it is. Right. So this is the notion, right? Is that black holes? What makes a black hole is that you've got something called an event horizon, a point of no return. Okay, to escape from the event horizon of a black hole. Yeah, just go ahead. You need to go. To escape from the event horizon of a black hole. So here's our singularity, literally a point in space where that sheet of rubber has been just pinched off, and where we're in a different or different universe, right? Surrounding this is a point of no return. Okay, so you encounter something called the event horizon, and the event horizon is a sphere, right? And then we're not going to get into rotating black holes because that changes things, right? It is a sphere of radius, and the radius is called the Schwarzschild radius. So I think we're to our first formula here, right? And to escape from here to an infinity, if a small mass were to escape from here to infinity is the place that's marked like that, right? Okay, and I'll put like a little, for the graphically sensitive here, right? An ellipses there, there we go. So a long way later, infinity, right? Okay, to escape from there to infinity, you have to possess a kinetic energy equal to the potential difference between here and infinity. And if you recall, that's V, that's G M, and this is big M here, right? G big M, so let's make this a small m, right? Okay, over R. That's the potential, right? We multiply that by the little m, and we did this like last fall. So if you don't remember that, there it is, right? Okay, and we did this with electricity. Now we're doing it with mass, right? Yes.
The singularity?
Oh yeah, baby, you're going to go in there. If you head straight in, baby, you're going to go in there, and then what happens to you is if it's a small black hole, it shreds you apart for your quarks. But your matter may re-emerge somewhere else in the universe, right? It could be another universe. It could be a gateway to another universe. There might be several universes right close up to ours, and so black holes might actually bridge from one universe to another, right? I mean, there's all sorts of crazy stuff. This is, this is giving science fiction writers a whole new genre to write about, yeah? It's like, you guys read the Golden Compass books? Those are just beautiful books, right? But, well, they're kind of dark sometimes. But anyway, that whole notion of the knife that cuts through and you can go in, we're not really very far from that. Yeah?
So, because I'm thinking that at the end of the horizon, you can't see anything past that because light can't escape, right?
Yeah, if you stand just outside the event horizon, nothing can get to you.
Yeah, but if you go past it,
you can see out.
Inside the event horizon, but still out, right?
Yeah, it's like those one-way mirrors, right? You stand inside and you see stuff coming toward you, crazily blue shifted. Right? Oh, that light's coming at me, right? Yeah. It's gained energy falling in there. It's still going the speed of light, but
as you get closer and closer and closer to the event of the singularity, you actually see more and more stuff out towards you. So it almost looks like the universe is growing in a sense.
I don't know. I'd have to think about that. Maybe. It's certainly going to be blue shifted as it comes into the toward the black hole. It's going to gain energy. Right. It's not going to go any faster, but it's going to be blue shifted, right? Well, anyway, let's derive our little formula here. This R here has to be the Schwarzschild radius, right? The m's cancel, so it doesn't matter what this little mass is, right? And then I'm going to do this, I'm going to make this speed be the speed of light, right? Let's make it be the speed of light, right? And then I can multiply this by c, or I can multiply it by 2, right? We're almost there, right? And then I can switch the rs and the c squared. Don't you love it when people do math like that? There we go. And there we go. This is the Schwarzschild radius. Okay, that's our first formula. So this is the radius of the event horizon. This is the mass of the very massive black hole, right? And then this is the universal gravitation constant, right? So that's 6.67 times 10 to the minus 11th, right? If we, yeah, there we go. Now the thing that's important to understand about black holes is that stars become black holes not by getting more massive. They actually become black holes by just getting small, right? So if we take the Earth and we crunch it down, the force of gravity on the Earth, right, is going to be gm1 m2 over r squared. What happens to the force as r gets smaller? It gets bigger and bigger and bigger and bigger, right? And so the gravitational field strength gets stronger. You have a greater distance to go. And so if we crush the Earth and made it about the size of a marble, only like God could do this, right? You know, no natural force is going to do this, right? But if we could just crush that thing down, right? Okay, it would become a black hole, but it wouldn't change its mass. The mass of the Earth would be a black hole if we shrunk it down to about the size of a marble. Okay, that's a crazy thing, right?
Does that ever happen?
Not for an object the size of the Earth. There's no, unless the Earth were to like enter a black hole and get crushed by the gravity of the black hole, right? That would never happen. The sun can't even make a black hole. It's not big enough. You need to be, at the time you collapse, to be about 3 solar masses, right? Okay, so here's our thing. If you solve this for the escape velocity, notice that r is in the denominator, which means that the smaller r is, the faster the velocity is. So that's what really happens, is we just make them small. Objects collapse, and as r gets smaller, the escape velocity gets bigger. When the escape velocity is equal to the speed of light, it becomes a black hole, right? So if we were to make the Earth 7/10 of an inch, that's an inch there, right? That'd be a big marble, right? But if we crunch the Earth like that, it would be a black hole, right? You have to crush it to within its event horizon, and then it's a black hole, right? If we took the sun would actually be 1.9 miles in radius. But remember, neutron stars are like the size of Portland. They're like 30 miles in radius. So even neutron stars are too big to become black holes, right? Gravity has to crush them even more, right? Okay. They're never going to become black holes, not all by themselves. You know, if there was a galactic collision, we might fall into the giant black hole that's at the center of either galaxy, right? Okay, so let's put this in your note. What's the maximum radius of a black hole that is 30 million times the mass of the sun? Right? Okay, so that's going to be, I'm just going to use this formula. It's 2 times 6.67. Right? And then that's our gravitation constant. And then we have to have 30 million times, so 30e6 times 1.99. Right? And then we have to divide by the speed of light squared, so 3e8. And then last period I was looking at this, I'm like, uh-oh, we've got a unit problem here, because there's kilograms squared in the denominator there, but there's only 1 kilogram there. So it's like, uh-oh. Whoa, I was having this cognitive dissonance. We have unit problems right over there.
What did you do?
Oh, there's another kilogram in there. I forgot about newtons. Isn't a newton a kilogram meter per second squared? That makes it all good. It's not likely that in a moment of absent-mindedness I would discover the eternal flaw of physics in front of a classroom full of kids. Okay, so times. That's right. Nobody else noticed this problem. Okay, times 1.99 E30 divided by 3E8 squared. This is like 8.8 times 10 to the 10th, isn't it? Yeah. Right. An astronomical unit, if I put it in the same scientific notation, an astronomical unit is 14.96 times 10 to the 10th meters. So they're both times 10 to the 10th, right? If you recall, it's 1.496 times 10 to the 11th meters, right? So this is amazing, right? A 30, and this is what they think lurks at the centers of all galaxies, pretty much, okay? Are these giant black holes that are just there because everything's fallen into them, right? This thing is more than half an astronomical unit in radius. Yes? It's like, that is a big black hole, isn't it? Okay? Something like that actually has such a gradual, when you cross into the event horizon, right? The curvature of space-time is so gradual that you could actually sail right into that thing without it tearing you apart. Now the problem with a small black hole is that as you go in, there's actually a tidal force. There's a difference in the force of gravity between your feet. Let's say you go in feet first, like you should do if you fall out of a raft. You know, keep your feet ahead of you, right? Push off the rocks. You know, if you go in feet first, the difference in the force of gravity between your feet and your head would be sufficient to rip you apart for your corks, right? Yeah, sideways would be the best thing, right? You know, yeah, there it is, right? Okay, so Stephen Hawking, and he said this in his talk, he said, if one were to